the golden ratio. So before we talk about the golden ratio, we're actually going to look at a sequence of numbers called the Fibonacci numbers. And it's going to start off just with a 0 and a 1. And to get the next number, all you need to do is add those two together. So 0 plus 1 is 1. And to get the next one, you just sum up the previous two. So this time we're going 1 plus 1, which is 2. Now we're going 1 plus 2, which is 3. 2 plus 3 is 5. 3 plus 5, 8. 5 plus 8, 13. 8 and 13, 21. 13 and 21, 34, and we're going to keep going, 55 and so on. Now, let's just have a look at what happens when, instead of adding the previous two, let's divide two at a time. So let's start off with 1 divided by 0, so taking the second and dividing it by the first. This is actually undefined. Anything divided by 0 is undefined. Now 1 divided by 1, looking at the next two, we get 1. 2 divided by 1, we get 2. 3 divided by 2, we get 1.5. 5 divided by 3, we're getting 1.666 reoccurring. Now we're up to 8 divided by 5, which we get 1.6. 13 divided by 8, which is 1.625. And if we look further down the track at two Fibonacci numbers, there would be 233 over 377, and we get 1.618025751, and so forth. So after just getting about four or five numbers in, we're getting 1.66, 1.6, 1.625, and then even really far in 1.61. There's not much change there, and it looks like we're getting something like 1.6. And this is in fact what's called as the golden ratio. None of these are the golden ratio, but they're getting closer and closer and closer to the golden ratio. And we're going to have a look at some interesting things. Let's disregard 0 as a Fibonacci number, but let's look at 1, and let's create a square that's 1 by 1. So this square is 1 by 1, and let's do another square that's 1 by 1 for the next Fibonacci one. So these squares are representing the ones. Then next to these squares, we can make a 2 by 2 square, because those two ones make a 2. Then next to this, we can make a 3 by 3 square. Next to all this, we can make a 5 by 5 square. Hopefully you can see that the length of this square is 2 and 3, which means the total's 5. So we just made a 5 by 5. Now we've got a 5 and a 3, which makes 8. Which hopefully you can see they're the Fibonacci numbers. So we get this 8 by 8 square. Now we can make a 13 by 13 square. And what happens is the lengths of these rectangles are getting closer and closer to being in the ratio of a Fibonacci, of the golden ratio, these Fibonacci numbers. It's just another way to represent that this side divided by this side is going to get us closer and closer to the golden ratio. And something nice you can actually do with this arrangement of the Fibonacci numbers in a square is make a nice spiral. So if we start here and draw a quarter circle, and a quarter circle, and a quarter circle, and a quarter circle, and a quarter circle, quarter circle, and a quarter circle, we can make this spiral here. And that spiral actually occurs in nature, and you can actually find that on a shell at the beach, or even a snail's shell. And these Fibonacci numbers also occur in nature as well. You'll find that the number of petals on a flower is always a Fibonacci number. So let's have more of a look at the golden ratio and trying to figure out exactly what it is. We know it's looking like it's 1.6 something, but I think we can do a little bit better. Now, before we do that, we're just going to look at this line segment. And the golden ratio can be kind of strange because it's almost defined on itself. So if this line segment was A and this one was B, this whole thing would be A plus B. And the golden ratio, well, the symbol for the golden ratio is a Greek letter called phi, and it looks something like that. And to define the golden ratio, we're going to say that it equals A over B, but only if that also equals A plus B all over A. So it can't just be can't just split this interval up any way we like. A over B also has to equal A plus B all over A. And you can actually muck around with this equation, because another thing to note is that 1 over the golden ratio actually equals B over A as well, like in this. So looking at this, which would also equal A over A plus B. And doing a bit of manipulation here, let's look at just this part here. We get A over B equaling A over A plus B over A, splitting up that fraction. And we get A over B equals 1 plus B over A. And then now we know that A over B, well, that's the golden ratio, equals 1, and B over A, that's 1 over the golden ratio. So you can see that the golden ratio is clearly defined on itself with this definition. But how can we actually find it? Another way to define the golden ratio is that it actually equals 1 plus 1 all over 1 plus 1 all over 1 plus 1 all over 1 plus 1 all over, and so forth. Now, let's try and figure out what the golden ratio is from this. Well, if all of this equals 1 plus 1 over 1 plus 1 over, this pattern actually just repeats itself. We can see that this part in here is actually the same thing as the golden ratio itself. It's 1 plus 1 over 1 plus 1 over, exactly the same as this entire expression. So we can say that the golden ratio equals 1 plus 1 over the golden ratio, exactly what we had before. So let's multiply every term by the golden ratio. So we have the golden ratio squared plus the golden ratio plus 1. Let's move everything to the left-hand side. So we have the golden ratio squared minus the golden ratio minus 1 equals 0. And this is just a quadratic, which we can now solve. So the golden ratio is going to equal minus b, so minus 1, plus or minus the square root of b squared, so minus 1 squared, minus 4 times a, which is 1, times c, which is minus 1, all over 2 times a, which is just 1. So we're going to get the golden ratio equaling minus 1 is 1, plus or minus the square root of minus 1 squared is 1, minus 4 times 1 times minus 1 is positive 4, and 1 plus 4 is 5, all over 2 times 1, which is 2. And if we just take the positive case, we're going to get the golden ratio equals 1 plus root 5 on 2, and this equals 1.618, so forth. But the exact value for the golden ratio is here, as 1 plus root 5 all on 2.